for this question, again, this is an old free response question. So they give us a balanced equation up here. We can see that NO and H2 are the reactants. It says experiments were conducted to study the rate of reaction. So it's just one step. Since it's just one step, we can't use the coefficients to write the rate law. So instead they give us data. So initial concentrations and rates are given in the table. And then A, part 1 says determine the order for each of the reactants, NO and H2, from the data given and show your reasoning. So remember that your reasoning could be math, it could be words. So when I want to determine the order for each of these, I want to see where does NO change while H2 stays constant. So we want to see where does NO change while H2 stays constant, because you only want one variable changing at a time. So I notice that NO changes from 3 to 4, while H2 stays constant from 3 to 4. So from 3 to 4, I notice that the concentration of NO goes from 0.001 to 0.002, so it doubles. And the rate, again, the way that they gave us this scientific notation, they made it easier for us to see because they did 0.3 times 10 to the negative fourth and 1.2 times 10 to the negative fourth. So they gave everything times 10 to the negative fourth, so we can just focus on the numbers in front. So from 0.3 to 1.2, that's times 4. Now if you're like, okay, well, what if I can't do that in my head? Well, then put it in your calculator. You can do 1.2 divided by 0.3, and that would give you 4. So as the concentration of NO doubles, the rate quadruples. So remember, we look at 0, first, and second order, typically. 0 order means that concentration, you can change it as much as you want. The rate's going to stay the same. First order, whatever you do to the concentration, you do the same thing to the rate. Second order, whatever you do to the concentration, you do that squared to the rate. So if we multiply the concentration by 2 and the rate quadruples, that makes NO second order. So determine the order. So I'll just say down here, NO is second order. As concentration of NO doubles, rate quadruples. Then we can look at H2. So now you want to look at where does H2 change, but NO stays constant. So H2 changes from 1 to 2, while NO stays constant. 0.002, so it doubles. The rate goes from 1.8 times 10 to the negative fourth to 3.6 times 10 to the negative fourth. Because these are the same, I can just focus on the numbers out front. 1.8 to 3.6 is also times 2. So I double the concentration, I double the rate. That means that H2 is first order. So then here I can say H2 is first order. So you could say, like, you might see it worded as H2 is first order, or the reaction is first order with respect to H2. That means the same thing. We'll say as the concentration of H2 doubles, so does the rate. And those are valid justifications. You can use words like this and then just show the math up in the table. So then part 2, write the overall rate law for the reaction. So the overall rate law is going to come from the orders that we just determined based on the data. Again, the reason we need to use the data is because this is just a single reaction. It's not a mechanism. Not an elementary step of a mechanism, it's just one step. So rate law, whenever you see rate law, just remember that it always starts with rate equals K, and then you have times the concentration of reactants. So I'm going to have times the concentration of NO squared, because it's second order, times the concentration of H2. If you want to put the 1 after H2 to the first power because it's first order, that's fine. But you don't need it because if it's not there, it's assumed to be a 1. And then part B, calculate the value of the rate constant K for the reaction, include units. So I'm going to do part B up here just so that it's easier to see. So with part B, you're calculating the value of the rate constant. So you want to look at what you've done so far. When you're looking at a free response question, you want to look at what have I done so far? What have I written so far that could help? Well, we've written the rate law. So I'm going to rewrite the rate law up here. And then from the rate law, we have the data that we can plug in. Doesn't matter which experiment you pick, as long as you show your work, you should get relatively the same value. I always just pick trial 1 because it's the first one. So from trial 1, I'm going to plug the data in to the rate law and solve for K. Because I have rate and concentration, I can plug that into the rate law. So the rate is 1.8 times 10 to the negative 4th. And this is moles per liter per minute. Remember, moles per liter is just molarity. So I'm just going to do molarity per minute equals K, which is what we're solving for. Concentration of NO, 0.0060 molar. Don't forget exponents. NO is squared times H2, 0.0010 molar. For your response, you always have a calculator on. So if I multiply, right, and I'm going to just do it all at once. So this is what I'm going to put in my calculator. 1.8 times 10 to the negative 4th divided by the quantity, 0.006 squared times 0.001. That's what it's going to look like in my calculator. 0.006 squared times 0.001. Get 5,000. Now it says include units. So if I look at my units over here, it was molar per minute over m squared times m. Now, if you just memorize them, that's fine, but just make sure you pay attention to the time. The ones in that table from before were seconds. This is in minutes. So if I kind of simplify this, I'm just going to bring minutes down on the bottom. One of the molarities will cancel. I get 1 over m squared times minutes, which is m to the minus 2 minutes to the minus 1. And the reason that it is m to the minus 2 is because this is a third order overall rate law. Third order overall, because 2 plus 1. Third order overall. If it was first order overall, it would just be per minute. Second order overall would be m to the minus 1, minute to the minus 1. Third order overall, m to the minus 2, minutes to the minus 1. It's just that molarity aspect that is changing. Any questions on the do now? I was trying to find one of these older questions that it's been a while since we've seen, just to make sure that we reviewed looking at the data, looking at if it doubles or triples. For you guys online, any questions? If you have any questions, type them in the chat. What I'm going to pull up next is to go over the question on what if a fast step is first. So this is just going over the question on looking at mechanisms and looking at a first fast step, or if your rate determining step is not first. So I just actually took a screenshot from one of the free response questions from yesterday and just put it up here. So this is showing a mechanism. So this is just a picture of a mechanism from yesterday, and this is 2 steps, right? So when we're looking at rate laws, I want to make sure we distinguish between a rate law and the overall balanced equation. Because when we say overall equation, right, the overall equation is when you cancel out and you add them together and it gives you reactants, yield products. So the overall equation, that's looking at your balanced equation. The overall rate law, that's looking at rate equals K times concentration of reactants. So if this question said, write the rate law, so I'm going to just make up questions off the top of my head. So let's say that part A said, write the rate law for each step. So if part A said, write the rate law for each step, that means that we're just going to say step 1 and step 2. We're just going to write the rate law for each step. It's not asking for the overall rate law. It's only asking for each step. So that means you literally take your reactants from each step and that goes into your rate law. Intermediates can be in an individual steps rate law. So for step 1, if I want to write the rate law, rate equals K, I have 2 NO2s. So I'm just going to do NO2 squared. That's step 1. Step 2, I want to write the rate law for step 2. Rate equals K times the concentration of N2O4. That's the rate law for step 2. That is okay as an individual steps rate law. Just wants us to look at each one. Now, if part B, so I'm just going to do part B kind of down here, said write the rate law. Rate law, not law. Rate law for the overall reaction. So write the rate law for the overall reaction, or write the overall rate law. That is when we have to look at the slow step. The slow step in a mechanism is the rate determining step. And so if we look at the slow step, we look at the rate determining step, that is step 2. So I would write rate equals K times the concentration of N2O4. However, at this point, intermediates cannot be in an overall rate law. They can be in individual steps, but they cannot be in an overall rate law. So when you have an intermediate in an overall rate law, and this almost always happens if the slow step is the second or third step, you're going to have an intermediate. Then you need to look at the fast step, set them equal to each other, and plug back in. So if I look at the fast step, I'm going to simplify a lot as I'm doing this. I'm going to do, all right, the fast step, I'm setting each side equal to each other. So I have NO2 times NO2 equals the concentration of N2O4. So I would solve the fast step for the intermediate. It already is. All right, it's already solved for the intermediate, which is N2O4. Plug that into the overall rate law. So instead of having N2O4 in the rate law, I'm going to plug NO2 squared in wherever I see N2O4. So rate equals K times NO2 squared. That's whenever you see an intermediate. If your slow step is not first, you will have to do this. The slow step is not the first step. You'll have to do this because you'll always have an intermediate. That's the whole point of a mechanism, is to have an intermediate. So if we look at labeling everything, and speaking of intermediates, N2O4 here is an intermediate. If I take a look at the mechanism, there is no catalyst here. You're identifying intermediates and catalysts. A catalyst would start as a reactant in step 1 and end as a product in step 2. We don't see that here, so there's no catalyst.
There's a catalyst, but you cannot put it in the rate law.
Right. If there is a catalyst, you also will not put that in the rate law. Just reactants. So that means that when you write the overall equation, so like if I want to write the overall balanced equation, that would be 2NO2 yields 2NO plus O2. This, only NO2 is what can be in the rate law, because that's the only reactant, which means that's all we can measure the concentration of. Yep. So that's looking at what if your slow step, your rate determining step, is not the first step. And then also just kind of thinking about terminology. Did that help?
Yeah.
Okay. Yeah.
Kind of forgetting what I asked you. But like if you had like we'll just say like plus fluorine for the products for step 1, and then it translated into step 2, how would you put that into the fast step setting an equal?
Like this?
Yeah.
Yeah. So that's just, a random, like if that was an intermediate. So because this, right, this would be over here. Well, if you think, so this one would be like, you'd have 2 intermediates. But if you think about it this way, it would look like this. Now you wouldn't see one like this on a test, but if you had 2 intermediates, you would just have to solve for N2O4 times F2.
Oh.
N2O4 times F2. So it would be the same way. The biggest thing would be if you had a catalyst. So if this was like, you had X as a catalyst, and you had like times X here, you just would not include that catalyst into your rate law.
Okay.
Yep. So during class today, we are on the shorter schedule. So second period ends at 10:31. So what we're going to do is we're going to go through some free response questions, some timed free response questions, because free response is going to be a better way to see more than just the conceptual ideas that were on the quiz. So speaking of the quizzes were posted back in ZipGrade. I left a comment in Google Classroom for the quizzes. So if you go back into that student portal, so it's the same information all the time, your ID and the access code. If you go into the student portal, there are posted, it says posted papers. You should see the Kinetics quiz 1 and the Kinetics quiz 2. If you click on it, you can see your answers and the correct answers. And then what I also did in comments on Google Classroom is I linked the Google Doc. There was actually the answer key that I typed in lots of extra information to. So you can go back and review those quizzes. I was kind of looking through, so the first quiz, we actually talked about the most commonly missed questions before. And from the quiz yesterday, there weren't like specific questions that stood out. It was just kind of questions here, questions there. But that's going to be one way to help you review, just looking at those multiple choice questions. And then there is a set of extra free response questions on the class website if you want to look more at the FRQs. So just remember that there's a lot of stuff on the website to help as well. So what we'll do is we'll get into the free response questions for Kinetics. If you need them still, they are over on the side counter. For the free response questions, you will want a calculator, periodic table, an equation sheet. As always, you can use your notes to help. And then you can also get into small groups. So if you want to get into small groups, you can. We'll go over them, we'll time them, and then we'll go over the scoring guidelines. Let's do number 2. All right, flip to number 2. So second actual piece of paper. Number 2 says 2016 FRQ number 5. So again, number 2 says 2016 FRQ number 5. And it says at high temperatures, the compound 1,3-butadiene reacts according to the equation. So I'm going to have you guys do 2016 number 5. I'm going to set a timer. I'm going to set it for 7 minutes. We'll go through the scoring guidelines. And as we go through, if you have questions, continue to type them in the chat as well. So for this question, now 5 minutes, well, wait, no, so we did 7 minutes. Okay, so 7 minutes. This was question 5 directly off of the 2016 test. So 5 years ago. And this was the entire question. So this should take anywhere from 7 to 9 minutes. So that's why I like timing, just so that you get used to that feeling. For this question, this started by giving you 3 graphs. So they gave you all the information up at the top, and then they gave you 3 graphs that had 2 trials of each graph. And part A said, for trial 1, calculate the initial pressure in ATM in the vessel at 625 Kelvin. Assume that initially all the gas is C4H6. So is part A related to kinetics? No. But this shows you that free response questions will pull in other topics as well. So if it's asking for pressure, right, nowhere else in the question did it say anything about pressure. So if you have to calculate pressure, it's probably a good bet that you're going to be using the ideal gas law. So for part A, you're using the ideal gas law, PV equals nRT. Now it says that you're doing it for trial 1. So what you need to be doing whenever you are looking at initial data, I'm going to switch back to what the actual free response page looked like. When you are looking at initial data, if you want initial concentration data, you should be looking at the concentration graph, right? No, this graph was not a straight line, so it wasn't 0 order. But if you want initial concentration, then you need to make sure you're looking at this graph, because the other graphs are showing you the natural log of concentration and 1 over concentration. So if they're just showing you concentration for trial 1, I'm going to start with 0.02 molar. And if we think about what that means, 0.02 molar means 0.02 moles per liter. So that takes into account N and V in the ideal gas law. So if we rearrange the ideal gas law to solve for pressure, it's nRT over V. Well, molarity means 0.02 moles over 1 liter. So there's N and V. R is the constant. T is the temperature that they gave us. And so this was 1.0 ATM. So the way that they actually scored this is they gave part A 2 points. 1 point for setting it up correctly, so meaning that you plugged everything into the ideal gas law, and 1 point for the correct answer. So in this case, if you plugged everything in, but then you did the math wrong, you still could have gotten one of the 2 points. So again, that was looking at gases, but just showing you that when it comes time for the AP test, free response questions will pull in other ideas, other topics as well. So part B, use the data plotted to determine the order with respect to C4H6. So for part B, the answer is that it's second order. It did not tell us to justify or explain, so you weren't required to say the plot of 1 over was a straight line. If you did, that's fine. But if it would have said justify, then you would have needed to make sure that you said that. So that was 1 point. Then part C. So there were different ways that you could solve part C. They showed 2 ways, but there was a third way, and they kind of noted down here as well. So part C says the initial rate of the reaction in trial 1 is 0.0010 molar per second. Calculate the rate constant K at 625 Kelvin. So there are 2 ways you could have solved this. The first way is you could have used the rate law. Right? And if you say, well, they didn't give us the rate law. No, but you figured out the order. You said that it was second order. So that would give us rate equals K times the concentration of C4H6 squared. Well, initial rate in trial 1, this 0.001, that's rate. You just need to look what the initial concentration was for trial 1. So if you look back at the concentration versus time graph, the initial concentration was 0.02 molar. And if you did that, you got 2.5 per molar per second. So just know that the liters over mole times seconds, that's per molar per second. Or you could have solved using the integrated rate law or the slope. So you could have looked at, let me go to this tab so everyone can see it. You could have looked at the second order graph. Now they wanted trial 1. They were talking about trial 1. So it probably would have been better to pick points from trial 1. Now, are you estimating here? Yes. But you could have tried to estimate the best you could to get the slope. So remember that rate constant must always be positive. So if you wanted the slope, you just pick 2 points. So if you picked this point, this was maybe 155 at 20 seconds and 50 at 0 seconds. And so you could have solved. Now, they told you in the scoring guidelines that if you solved for the slope, and if you got 5 per molar per second, you still would have gotten the point. Because it talks about adding in the coefficient. But if you chose to use the slope, they would have accepted either 2.5 per molar per second or 5 per molar per second. And if you got something close to that, that was okay. So 2 different ways you could have solved. Both ways were acceptable. So that was looking at a shorter free response question. All right, 4-point short free response question. The next question that I want us to look at is actually number 1. So I'm going to flip back to number 1. Notice that parts A, B, and C are not related to kinetics. This was the number 3 question on the 2017 practice exam. The practice exam is the makeup exam that they give for people that don't take it the first time. So this was a different form of the 2017 test. Parts A, B, and C don't deal with kinetics, but it's still questions. You should be able to do all of them. So on a normal day, we would have done this entire question. Now, I want you to start where it says ozone can oxidize HSO3- as represented by the equation below. So when you're looking at number 1, right, A, B, and C, you can make yourself a note to look back at later. You're going to start right here where it says ozone can oxidize as represented, because then it gives you some information. That's why I'm telling you to look at this before you flip to the back page. Then it gives you a graph. So you're going to read through this information, and then you'll answer part D. So since we're just focusing on part D, I'll do 8 minutes on the timer. So what we'll do is we'll go through the scoring guidelines to this 2017 question, and then that's probably all we're going to get to today just because it was shorter class periods. So for this question, again, parts A, B, and C. I have the scoring guidelines here, and I'll show you where you can find these. So if you want to do the rest of them as review, you can. But you'll see that A talks about ozone, has you draw Lewis structures. You know how to do Lewis structures. Part B is asking you about the shape. So asking you the shape of ozone. Part C is asking about bond enthalpy. So when we did bonds broken minus bonds formed, we did that when we did thermochem. So parts A, B, and C, we have done all of those already. And this also shows how it was scored. So parts A, B, and C was actually 5 points already. So long questions, questions 1, 2, and 3 are long questions on the AP test. They are worth 10 points. They take anywhere from 15 to 20 minutes. And so that's why I gave us about half the amount of time, because we were just looking at half of the question. Then we get into part D. So it has all this information about ozone, and then it gives us this graph. So notice that the graph is concentration versus time. So this graph is just concentration versus time. And so then part D says the data is consistent with the following rate law. Rate equals K times the concentration of O3. So since we have concentration of O3 versus time, it's okay that it's not a straight line. This being a straight line just would mean that it was 0 order. Just because it's not a straight line doesn't mean you can't use the graph still. So for part 1, based on the graph, determine the half-life. So to determine the half-life, you can just use the graph. Initially, you have 1 times 10 to the negative 5th molar. Half of that would be 5 times 10 to the negative 6th. So you go 5 times 10 to the negative 6th. And if you're like, I can't do that in my head, you have a calculator on the free response. You can do 1 e negative 5 divided by 2. Find half of it. Half of it, 5 times 10 to the negative 6th. Right, that's 0.01 seconds. And then you could find it again if you wanted. So that'd be 2.5 times 10 to the negative 6. Notice that's another 0.01 seconds. So the half-life is just 0.01 seconds. You can use the graph to determine the half-life. Now, here's the important thing here. This tells us that it's first order. The rate law tells us that it's first order. Remember, the importance of a first order reaction is that the half-life is constant. So throughout the entire process, the half-life is constant. Part 2, determine the value of the rate constant for the rate law, include units. So notice this was 2 points. 1 point for the value, 1 point for the units. So if you only had the value and you forgot the units, or your units were incorrect, you still could have gotten 1 of the 2 points. And this is also based on your half-life. Let's say that you got your half-life incorrect, but you used what you got in part 1 for part 2. You could have still gotten both points for part 2. It's conditional grading. So you're just using the half-life equation, 0.693 over K. You manipulate, you have K equals 0.693 over T1 half. 0.693 does not have units, 0.01 seconds. And so you get 69 per second. Again, that was 2 points, 1 point for the value, 1 point for the units. Part 3 says, considering the relative concentrations of reactants, briefly explain why the data is also consistent with this rate law. So both of them being first order. So the data is consistent with both of them being first order because the concentration of HSO3 minus remains essentially constant. during this experiment. So HSO3 minus is not changing the rate very much when we're changing O3. So the data is consistent because the concentration remains essentially constant during the experiment. And then part 4, briefly describe an experiment that could provide evidence to support the rate law given. So this is saying if this is the rate law, if both of them are first order, how could we verify that? So it's thinking about what we did in the do now. So we can repeat the experiment with different initial concentrations of HSO3 minus. So we can hold O3 constant and change HSO3 minus. We can look at how the rate changes when we change the concentration of HSO3 minus. So we can repeat the experiment with different initial concentrations. So that was it for this one, right? Just part D was the kinetics part of the free response. And so biggest thing again is going back and remembering that you can use the concentration versus time graph. Now, could you have solved part 2 differently by figuring out the slope? Yeah, you could, but you could also just use the half-life. So something that I want to just point out is if you go to the class website, so you can type in ptapchem.com and you go over Unit 5 and you click on review. So if you click on Unit 5, this is going to take you to the notes, the playlists. So everything that I record goes onto the practice playlist, which is also linked in Google Classroom. But all of the practice videos are here. But if you go to review, so if I click on review, this will take me to all of the answer keys and it will show all of the free response. So you have the test review. Here are all the free response questions. All right, so there's everything that you need.